Okay, welcome everyone. Good morning, good afternoon, good evening. Just wanted to welcome you to today's ASK Online Academy webinar titled Exact Port 3D Filters for Unmatched Reliability and Consistency. Today's speaker is Mr. Dave Heckman. He is the Technical Product Manager for Feeding Systems in North America. And my name is Lee Horvath. I'm the Business Line Manager for Feeding Systems in North America. I will be your host today. Before we begin the webinar, a few organizational notes for you. So due to data protection reasons, no clear names are visible, and the image and camera transmission is also deactivated during the webinar. You can submit questions if you have them via the chat function. So there's the box at the bottom right, and then we'll try to answer as many questions as we can after the webinar is over. If we are not able to get to all the questions, we will answer those and they'll be addressed by our experts afterwards. We will send a recording of the webinar to all the participants today via email after the webinar is over. So right now, I will hand the reins over to Mr. Dave Heckman, who is going to talk to us about 3D filters. Dave?
Thank you, Lee. Just to review the agenda today, we're going to review why foundries use filters, some traditional foam filter production techniques, some new development and product development with filters, some 3D case studies, and then a conclusion. So why do foundries use filters? Foundries use filters for two main reasons. First, filtration of oxide particulates contained in the molten metal, and two, to improve the laminar flow of the molten metal as it enters the casting cavity. When we look at this drawing, we can see the three main ways that oxides are removed with foam filters. First, oxides can be physically removed with any oxide that's larger than the pore size being sieved at the filter face location. Secondly, oxide segregation is allowed due to the fact that oxides typically are less dense than the metal being cast. This density difference creates a buoyancy that, due to the pressure drop of the reticulate filter, allows modification of these oxides in the runner system or the reservoir above the filter. And thirdly, the chemical bonding. Any remaining oxide materials that flow through the filter have a probability of contact due to the reticulate structure, and when they contact the filter surface, they sinter or chemically bond and be removed from the metal, and clean metal is allowed to be poured into the casting cavity. When we look at this representation or cross-section of a filter, we see some of the large oxide slags being trapped on the filter surface. These oxide inclusions in slag are too large to be transmitted through the pore size of the filter. When we zoom in on a filter web, we can see some of the removal of the micro inclusions. In this image, the metal is flowing from left to right. The dark layer is an accumulation of micro inclusions on the filter web surface. Analysis of that material shows it to be high in alumina oxide. This is common for steel alloys. The refractory that's used in steel foundry processes is high in alumina. The furnaces and ladles are made of alumina refractory, and these materials can be easily eroded or spalled during the process. Additionally, aluminum is used to deoxidize steel. The aluminum reacts with the oxygen in the steel metal creating residual alumina oxide. These aluminum materials need to be filtered with the reticulate foam. In this image, you'll see a scale on the bottom right of 100 microns. This gives us a relationship that the oxides being trapped on the upper side of the filter web are anywhere from 2.5 to 25 microns. The bottom right representation shows the area of a filter web versus the oxide particulates that it's capturing. The yellow area represents a 10 ppi foam structure, which this filter is. The two smallest black dots represent the inclusions of 2.5 microns and 25 microns. It's pretty easy to see that these inclusions are too small to be physically removed. Oxide bonding or chemical bonding to the filter web needs to occur for these materials to be removed. When analyzing or reviewing laminar flow improvement of molten metal through filters, one can use water modeling. Before simulation softwares were available, many steel foundries used water modeling to simulate any issues with turbulence or reoxidation in their runner systems or casting cavity. The kinematic viscosity of water is very similar to many ferrous alloys. These two fish bowls represent a direct pour application. So the casting on the left would be a direct pour without a filter, where a lot of air entrainment, turbulence can be seen. The reaction of oxygen to the metal can reoxidize and create oxides and slag in the casting cavity, also creating erosion. The casting on the right has a filter, which creates a metal head and promotes oxide segregation. The reduction in Reynolds number also allows a laminar flow of the molten metal into the casting cavity to limit any reoxidation or turbulence as the casting fills. I would like to talk about some foam filter production and filter types. Foam filters are produced when compounds are mined from the earth. They're either chemically or thermally refined to provide the raw materials. Four of the raw materials are here on the left: zirconia, alumina, silicon carbide, and mullite. These raw materials are then combined with other components in a water-based slurry that is then taken and applied to a foam precursor material. The precursor material is selected for pore size and then cut to a size and shape. The slurry is then applied and allowed to dry. The ceramic coated foam is then fired in a high temperature kiln. The fired ceramics are then removed from the kiln, inspected for quality, and shipped to a variety of casting producers. Four of the raw materials can be seen here: a chemical grade is zirconia, thermal grade is zirconia, alumina, and silicon carbide filter. Foam filters are classified by dimension and pore size. The pore size designation is PPI. PPI stands for the average amount of pores per linear inch. Common PPIs are 10 through 60 PPI. One of the most common and largest pore size possible is the 10 PPI foam designation. The 10 PPI cannot go any larger due to the restrictions in the polyurethane foam production. The chart on the right also shows that the 10 PPI has the most variance in the pore sizing. A 10 PPI has a specification from 1700 to 2400 microns. Looking at the image below, you can see the range of 10 PPI filters from open to fine. The filter on the left side has an average pore size around 25 or 2400 microns. The filter on the right side has an average size of 1700 microns. These are all filters that are in this 10 ppi specification, but the variability within the 10 ppi can cause some issues with large ferrous casters. Many of people that produce large ferrous castings tend to pour their castings at lower pouring temperatures. The inconsistency of a 10 ppi pour size with this lowering pouring temperature can cause issues with priming the filter and/or misrun. This lack of repeatability in the foam filter process for large ferrous castings is sometimes too high of risk for these casting producers to try with their castings. With the advent of additive manufacturing, custom cell sizing, dimension, and structure were achieved. This led to more repeatable capacity, flow rates, and priming efficiencies. The ASK product name for a 3D filter is called the Exact Pour filter. I would like to take a second to show a quick video on ASK's Exact Pour filters. When comparing foam filters to the new ASK Exact Pour 3D filter, one can see inconsistency with the foam reticulus pour size. This can lead to variation in flow rate and capacity. Unsupported tendrils are fragile and can be damaged in shipment or mold insertion. This can allow filter bits into the casting cavity. The Exact Pour filter was designed to fully support its filter webs with unlimited cell sizes available. These filters are also offered in many customized shapes and sizes. The fully supported structure allows for greater strength, while increased cell size improves capacity. Since the Exact Pour's printed design still utilizes a reticulate structure, it achieves excellent laminar flow and inclusion capture with increased flow rate capability. A variety of add-ons, including edge coating and gaskets, are also available. The Exact Pour filter offers a variety of improvements over traditional reticulated ceramic filters. Please visit ask-chemicals.com for additional information on these products. With the design of the Exact Pour filter, a new cell designation was needed. This designation was to be MMC, which stands for millimeters per cell. A 10 MMC filter would have a cell size of 10 millimeters. The additive manufacturing process allows ASK the ability to increase or decrease the size of the cell structure. With increased cell size, increased capacity becomes more repeatable. On average, ASK recommends a like-size filter from 3D printed to foam to have a 300% increase to capacity. PPI and MMC have an inverse relationship. If you increase the number of PPI, you decrease the size of the cell. With MMC, as you increase the number of MMC, you increase the size of the cell. The right side chart shows a pressure drop comparison of pore size versus cell size, which equates very similarly to flow rate. The samples of pore size and MMC were put on the chart to create a trend line. If you look at the red line, which is derived by the foam samples, you can see that not many of the foam samples actually touch the trend line. This is due to the inconsistency of the foam process. The blue line, which is the Exact Pour line, has nearly every sample touching the trend line. It just shows the repeatability of the 3D process over a foam filter. The exact pour materials are made with two different type of raw materials. First, the PSEM, which is a chemically derived zirconia that is white in color. And secondly, a PSZT, which is a thermally derived zirconia, which is tan in color. The exact pour filters are implemented in a very similar way to foam ceramics. The inline implementation can be vertical or horizontal, while additional implementation techniques such as direct pour or ceramic tile are available. Horizontal application of a filter is parallel to the parting line. The bottom right image shows two castings, one with a filter and one without. The upper filter, or the upper casting without a filter, shows that some of the oxides are trapped on the cope side surface of the runner, but the majority of inclusions make it into the bottom casting with a filter shows the pressure drop above the filter, creating a lot of modification where many of the macro inclusions are trapped on the cope side surface of the runner or the reservoir above the filter. The additional inclusions are removed by the filter and clean metal is allowed to flow into the casting cavity. With vertical orientation, we can see the pressure drop, allowing a lot of the macro inclusions to modify to the cope side surface of the runner system. Though there is not a reservoir with a vertical orientation, the remaining inclusions are removed from by the filter and clean metal exits to the casting cavity. An advantage of a vertical system is that it's easy to do trials. The two right images show a before and after of a runner system that wanted to do tests with filters. A filter blank can be applied to the runner system, which is oversized to reduce plugging issues and any flow rate variations. The gating ratio for these trials are typically 4:1. The filter can then be placed into the runner system. Test castings can be produced and then reviewed. If the castings show benefit, the vertical application can continue, or one can transition to a horizontal application to see if there will be further improvement. If no improvement is realized, the filter blanks can be removed and traditional casting techniques can be reinstated. When reviewing direct pour applications and ceramic tile applications with exact pour filters, we can see the top right picture is an excellent example of a filter being used for direct pour. The filter is a traditional foam filter, but an exact pour filter can be implemented similarly. This tapered filter is placed in a neck down riser where the metal will be poured into the filter, allowing the oxides to be removed and modification of the metal into the casting cavity. Once full, the filter will be allowed to float, and that will maximize the cross-sectional area of the riser with the casting and provide efficient feeding. With tile gating systems, filter housings can be applied. Tubular and cylinder filters are available for this type of product. ASK has designed an exact fill housing system to encase these type of filters. The filters that are produced for these systems can be either foam or 3D printed exact pour filters. The tile will be connected to an inlet. The metal will be allowed to filter from the OD to the ID and then directly into the casting cavity. An example of this is this 15,000 pound Ferris pump housing. Traditionally, they had used a series of filters horizontally applied to maximize capacity. Instead of having one filter, there are 10 filters in series to handle the 15,000 pound capacity of this casting. The metal is filtered adequately, but upon exit, it is allowed to cascade 1 meter down to the bottom of the runner system. When this happens, gravity overtakes the pouring system, and all the laminar benefits are removed from the filter. When using an exact fill housing system, the filters can be placed at the bottom of the contacts, allowing a pressure drop that backs up the runner system and reduces any reoxidation potential due to the acceleration of gravity. The runner system remains full, the alloy is filtered effectively with the filters, and laminar flow is created at the base of the contacts. I would now like to review a few case studies of the exact pour filters. The first study is with a mill liner casting, with the customer induction melting, pouring from teapot ladles, having casting weights from 500 to 17,000 pounds. This customer is producing wear-resistant steels and using a traditional parting line gating system, but is very interested in direct pour applications. The initial situation at the customer is the customer is not using any filters, but they have tried reticulated foam filters in the past with unrepeatable success due to their large casting pour weights. This foundry was experiencing an increase in quality requirements and demand for their castings, yet they had reached capacity. To supply this increased casting quality and supply demand, the foundry would need to find ways to improve yield without lowering casting quality. Direct pouring with a 3D filter could be very advantageous. The initial trial plan was to select a casting to be trialed with inline filters. The casting would then be reviewed for improvement in quality and prove the concept of the filter's effectiveness and repeatability. A 6x6 12.5 mmC filter was designated for this test. If successful, the second trial would be a direct pour casting to be using a tapered filter and a large neck-down riser. The first casting selected for the inline filter trial was a chromoly steel with a pouring temperature of 4,500 degrees. The pouring weight was 8,800 pounds with a pour time expected to be 45 seconds. 3 of the 6x6 12.5 mmC filters were to be used. 24 castings would be produced, with 8 castings using filters and 16 castings being poured in the traditional non-filter design. The gating system for these castings with the filters were shortened to improve yield and better cost justify the filter. The gating system was reduced by 50% to improve the yield. Using magma, a velocity reduction into the casting allowed for less turbulence and reduced the potential for any erosion or reoxidation. And due to the yield improvement and better thermal fill, one less riser would be required to feed the casting. After pouring, the castings were reviewed, and the filter castings had a very good surface. Non-filtered castings had a lot of slag and inclusions on the cope side surface, which produced 50% rejection for slag and inclusions that had to be either sent to rework or scrapped. The filtered castings 100% passed inspection and was sent to final machining. A secondary improvement was noted when the casting machining of the bolt implementation was reduced. After the success of the first test, a direct pour casting was selected. This was a mill liner casting of chromoly steel. The pouring temperature was 2,756 degrees with a pouring weight of 4,600 pounds. Pouring time was just under 50 seconds, and we used a 5.5 tapered filter, 5.5 inch bottom OD tapered filter that was 10 mmC. This filter was placed in a 10 by 5 by 12 exothermic neck-down riser. Some images of the casting are on the right with some great surface finish and a clean knockoff area. After reviewing the casting results, the castings poured successfully with quality improvement due to oxide and slag reductions. Yields were then increased 7.5% by removing the gating system, which allowed for increased production. As a filter program was further implemented at this customer, capacity optimization was realized. Yields were further optimized by finding the max capacities that we could use with direct pour filters and inline filters. For direct pour, we sized the filter 1/2 inch over the bottom ID of the riser, and the below capacity charts were created. The capacities that were used in the below charts is around 150 pounds per square inch. This is a remarkable increase when you regard it or compare it to foam filters. Foam filters typically have a recommendation of around 27 pounds per square inch for these type of alloys. This is over a 500% increase in ASK's recommendations. The final results at this customer with the casting quality was increased, lowering the need for rework and additional machining, while yields were improved 3.5% to 7% depending on the filter application or orientation. Due to these increased yields, production increases were realized without any additional capital investment. The next case study is an alloyed steel mill roll. This customer is arc melting with lip pour ladles. The casting weight ranges from 5,000 to 30,000 pounds. They are producing high alloyed iron that is centrifugally cast. The initial situation is the foundry currently uses foam filters on single alloys poured up to 13,000 pounds. This foundry is experiencing quality improvements with the foam filters, but wanted to extend that benefit to larger castings or castings that had multiple pour alloys. This foundry has restricted accessibility to the pouring tundish and overhead crane location with strict timing requirements with pouring. The trial plan was to find a casting around 12,000 pounds and use an 8-inch round 15 mmC tundish filter. The casting will require a large amount of high alloyed chrome iron with a 6-minute dwell time, and then a smaller additional pour of an alternate alloy after. The selected casting was a high chrome iron poured at 2665 degrees Fahrenheit. The first pour totaled 9,700 pounds. The ladle was then taken back to the furnace to be filled with an alternate alloy. During that time, the tundish and the filter were put back on preheat to maintain temperature, and the dwell time was 6 minutes. After the 6 minutes, 2,000 pounds of an alternate alloy was poured to complete the 11,700 pound casting. If you look to the right, you can see the filter, the 8-inch 15 mmC filter after pour. There was a lot of oxides, inclusions, and slag that were trapped on top of the filter that was removed from the pouring system. The filtered casting experienced approximately 50% reduction for slag inclusion indications, resulting in less rework or scrap. This customer also pours an additional 25,000 pounds of ductile iron as backing metal after solidification of these filter surfaces. ASK is working with this customer on filter development for this application. The last case study is a stainless steel yoke. The customer is using induction melting with a teapot pouring ladle. Casting weights range from 1 to 1,200 pounds. The customer pours a variety of steel alloys, focusing on stainless steels. And though they use a lot of traditional gating systems, direct pour is their preferred method of pouring. The initial situation is this foundry has been using reticulated filters for many of their current castings. A customer for the foundry had requested them to pour a casting that is above their current limit of 3,000 pounds. The foundry has restricted metal, ladle, and filter capacity. So the plan was to use a double ladle pour to achieve the 3,500 pound pour weight. Since a foam filter with their experience would not be successful, a 3D direct pour filter was selected to trial. The steel yoke had a casting alloy of CF3M stainless. A pouring temperature of 2,825 degrees Fahrenheit was selected to pour the 3,500 pound pour weight casting. The tapered 8.5 inch bottom OD filter with a 10 MC was used in the 12 by 6 by 12 neck down riser. The 3,500 pound casting poured completely and used a 30-second dwell time between the two pours. This casting is the largest total on-site pour weight for this customer. The first casting passed inspection requirements and more castings are scheduled to pour. To review some conclusions, 3D exact pour filters have a remarkable increase in capacity and flow over traditional reticulated foam filters. The exact pour 3D's more open and repeatable cellular structure produces higher consistency with added confidence for large ferrous casting applications. And though traditional foam filters still maintain a cost-effective value with small to mid-range steel castings, the exact pour 3D filters provide advantages in larger applications, which would be 2,000 pounds and higher, due to the successful repeatability of the filter's performance. Thank you for your attention.
All right, Dave. Thank you very much for that informative presentation on 3D filters. Looks like we do have a couple questions that we can take right now. The first one is, what is the typical increase in capacity for a 3D printed filter?
Okay. Typically, when you go in from a like-to-like size, say if we started with a 6x6 and went to another 6x6, we recommend, ASK recommends starting with a 300% increase in the capacity over a foam filter. On ASK's website, there is a brochure for the exact pour filters that have these charts and those recommendations available.
Okay. Next question is, what cell size would ASK recommend for low carbon, low alloy steels?
Okay. Good question. Typically, I would start with a 12.5 mmC for a low carbon, low alloy steel. These steels can tend to be very thick and drossy. So we want to start a little bit more open. Obviously, the more open we go, the less filter efficiency that we could have. So I would start with 12.5 mmC. If you have adequate capacity with that filter and you needed to improve the quality or oxide removal or inclusion removal, you might look to go finer after having success with the 12.5 mmC.
Great, thank you. The last question I'm seeing is, does the cell size affect the efficiency of the 3D filter?
Yeah, similarly to what we just said, the larger you make the cells, the less effective the filter is going to be. So we can make these cell sizes 37 millimeters, but then you can throw golf balls through them. So you need to have some type of efficiency or probability of contact. The biggest cell size we've made is around 15 to 17.5 mmC, and these are for very large applications that were more concerned with the laminar flow efficiencies. So for most of the steels, I would say low carbon, low alloy steels, I would start right around 12.5 mmC. Stainless alloys, maybe looking at a 10 mmC. And if you're getting into some very fluid, very high alloyed ferrous alloys, you could probably look to 9 or 8 mmC.
Okay. The next one is, what is the predicted yield improvement between standard foam filters and 3D printed filters?
That would be dependent on your orientation. If you can just remove or eliminate, a third of your filters, you could probably reduce your runner systems from 3 filters down to 1. So you'd have the reduction of runner system and filter space needed there. If you were looking at direct pour, you could size it due to the riser, and everything would be just the yield improvement based off the elimination of the runner system.
All right. Next question is, what size would you recommend for greater than 7,000 pound pour weight of low carbon steel?
Okay. It would be dependent on how you wanted to implement it. But for a 7,000 pound pour weight, we would probably want to start with around 3 6x6s if we were going to do inline. That's pretty large for a direct pour, so they're probably not going to want to direct pour that casting. But you could also tile gate it. So if you use tile or the exact fill housings, you might be able to go with 1 or 2 150 millimeter exact fill housings, depending on the capacity. When you get to castings of this size, it would be very advantageous to do a preliminary filter capacity test. So taking a smaller filter, maybe a 2x2 or a 3x3, pour it with your alloy and just see how much you can maximize and pour through that filter will give you a relationship to what you can extrapolate in surface area to a larger filter. So it may be easy or advantageous to pour on 1,000 or 1,500 pound pig with a 2 or 3x3 filter, just to see what the repeatability or what your foundry's alloy performance can be.
Okay, thank you. We got a couple more questions here. Why do zirconia-based filters have more metal capacity compared to silicon carbide filters of the same dimensions?
I wouldn't say that zirconia has more capacity. I would think the capacities would be similar. And in fact, I would say zirconia would probably be a little bit less. The real reason people tend to try to use silicon carbide over zirconia is just the cost difference. But the affinity for zirconia to bond and remove oxide inclusions is usually higher when related to silicon carbide. We just don't make a silicon carbide in the additive manufacturing process because it doesn't have as much value. And zirconia is the strongest and best filtering medium that we have.
Okay. I think we got one more question here. Are there any differences in durability between foam filters and 3D filters?
When we do, say, like a 3-point bend test, the strengths are very similar, but with the more open pore structure, you also have a reduced pressure drop. So you get less tensile forces when you're doing a pour. So the 3D filters tend to be more reliable from a direct pour standpoint or an inline standpoint, these large alloys, because they have less pressure drop. And as you remove more inclusions or plug up that filter, that tensile force increases, which could lead to the foam filter failing. Doesn't mean that the foam filters are bad. They just tend to plug up a lot easier, and that increases that tensile force and can create more failures. So I would say that the 3D exact pour filter will be a stronger filter in practice.
Great, thanks, Dave. All right, I think that's it for the questions for now. And we're basically out of time. So we've reached the end of our webinar for today. I hope you enjoyed it, and you're welcome to join any of our forthcoming webinars. If you visit our website, you can see the next dates for the ASK Online Academy, as well as recordings from past webinars. In addition, you'll find a lot of other useful information like our product and support area, where you can find our product finder and other technical papers on current issues. So with that, we really appreciate everybody attending today. We're very, very appreciative of your time, and we wish you, as we go into the holiday season, a safe and happy fall, and we look forward to your evaluation of this webinar directly after the webinar is done here. So thank you very much, and we'll see everybody very soon. Take care.
Thank you all.